So Katekani, floor is yours.
Good afternoon, everyone, and thanks for the introduction, Prof. My talk is titled Nanosensors for Food Safety Applications. The outline of my talk covers the background of gas sensors, why the research on gas sensors, choice of sensing layer, research interest, strategic approach, outputs, and summary and acknowledgements. So gas sensors form part of our everyday living and working spaces. We use them for many applications. So a gas sensor can be explained as a transducer that converts a certain parameter to another parameter. That is a non-electrical parameter to an electrical parameter. So gas sensors, they rely on the method of transduction. So we have different gas sensors that can be optical, electrochemical, and chemiresistive gas sensors. So this study focuses on the use of chemiresistive gas sensors, which uses a semiconductor-based oxide as the sensing layer. So what happens is that we look at how the resistance of the material changes when in contact with a certain gas analyte. There are different sensors parameters to look at. There's the limit of detection, your response, how your material responds, how long it takes for it to respond and recover back to the baseline, how stable is it over a period of time, and how reliable is it. But with the reliability, we actually just look at the sensitivity, selectiveness, and reproducibility. So there are challenges with the chemiresistive gas sensors, which are using the semiconductor metal oxides, is that they suffer from high power consumption because they operate at high operating temperatures, which is above 300 degrees Celsius. And they also struggle to select a specific gas among other gases in a room, sort of. And also, the stability is a problem because you find that after a certain a certain period of time, like say maybe a year, the sensor response, there's a drift in it. So the stability is also a problem. So there are approaches that have been tried by different researchers out there to overcome these challenges. And some include morphology engineering, doping with foreign materials onto your main material, and surface sensitization using noble metals. Okay, so the gas sensors classified by technologies, we have the solid state, which is the ones that I mentioned, the chemiresistive gas sensors, electrochemical, infrared, and optical. So looking at the market trend, you can see that there is a compound annual growth rate of 6.81 from 2019 to 2026. So meaning that the use of this gas sensors is still going to increase. So we still have a room to play in that market. So, okay, why nanosensors for food monitoring? So when it comes to food has got different shelf life stages. That is the production, storage, shipment, and also consumption. So during these different kinds of stages, your food stuff, they emit certain gases or VOCs, and those gases or VOCs, they can be indicators of the status quality of your food. So different types of food emit different types of gases and VOCs. So for example, when it comes to muscle food, like your meat, you can use the gas ammonia to detect whether it's still fresh or not. And for fruit and vegetables, you can use ethanol to check if it's still in a good quality state. And other than spoilage, we can also use some of these VOCs to check the level of ripeness of your food. You can use VOCs such as ethylene. Okay, so the strategic approach for this research work, we'll start with the the main research goal. The main research goal is to develop a sensitive, selective, and reliable nanosensor for rapid detection of VOCs, your ethylene, acetone, and ethanol, but we mainly focus on ethylene, and ethanol. So the research objectives include design of nano-enabled base sensors, to investigate the nano-enabled base gas sensors performance towards the VOCs emitted by fruit and vegetables as per application specifications, correlate the gas sensing performance to ripening or spoilage of fruit and vegetables with focus on ethanol, acetone, and ethylene. So now I'll take you through some of the results we obtained when we're doing our testing of our materials. So we are using different semiconductor metal oxide in our group. So this is just one of the metal oxides, which is a lanthanum carbide. It's in nanofibers. Since we are using nanomaterials to apply nanotechnology for these materials. And the reason why we're using nanomaterials is because these nanomaterials, they offer a high surface area, which is very beneficial for gas sensing, since sensing is a surface mechanism. So it needs, the larger the ground to play on, the higher your response of your sensing performance. So these ones, these results that I have here, were motivated by some work we did in 2020, which we published in Sensors and Actuators. So then we were focusing on the pure lanthanum cobaltite. So we were actually playing around with the morphology. We were doing the morphology engineering. So, and then this one, it's a modification of that, whereby now we introduce a foreign material into our pure lanthanum cobaltite. So, this diagram here shows this is the behavior of our sensors when now we expose them to different gases. We expose them to ethanol, acetone, methanol, isopropanol, ammonia, and others at a specific concentration. And in this case, we focused on 40 ppm. And also at a specific temperature. So from the diagram, one can see that the highest response we obtain is that for ethanol, and with the red, they're showing the highest among all of them. And then the red is the one which was loaded with the highest of the foreign material, which in this case we added, it was cerium. So for us to continue with the sensing performance study, we have to do a temperature dependent study because the performance of gas sensor relies on that. We want to see where are we getting the optimum performance of our sensor. So we subjected the sensors to different operating temperatures ranging from room temperature to 180 degrees. And this one, the red there, it shows it optimum operating temperature at 100 degrees Celsius. So all the testing was done at this temperature, and the other sensor specifications were, like, we exposed the sensor to different sensor specifications. We started with the concentration, which was between 2.5 to 40 ppm, and at that operating temperature. So, as Prof mentioned that it's combination of chemistry and physics, so this is where the physics come in, the application part. So now we want to see, okay, we said it's a chemi-resistive gas sensor, which looks at the resistance. So that resistance, when we take it, we then convert it into a response to give us our response. So here, this first diagram shows how the material behave when now you introduce different concentration of your target gas, which in this case is ethanol. So we see that when you introduce your target gas, there's a sharp increase of your response, and then it reaches a steady state, and then it drops. So when it increases, that's the response, and then when it decreases, that's the recovery. So we can see that the response of our material increases with the increase in the gas concentration, which is a very good parameter of a good sensor, because it shows that it can operate, it can actually detect a longer range of your gas concentration. So the response and recovery time, it revealed that we have, for the sensor, which is highly loaded with the cerium, we had response of 12 seconds and recovery of 32 seconds, which is very good. So we also have to check whether the response or the signal of your sensor can actually repeat itself. So we do many cycles of the same concentration to see if it can repeat the signal. So in this case, we're focusing on the highest performing sensor, which was the red one. And then it shows that actually the signal can be repeated, which is very good for application in gas sensors. Another factor is the stability. Remember, I mentioned that a sensor has to be able to reproduce the same signal over a certain period of time. So with our sensor, we managed to do the stability for a period of 60 days. And we realized that our sensor was able to retain 74.5%. It lost 25.5% of its response. And also, but we're still gonna do longer time just to see where is this still gonna drop or it's still gonna just stay here. So another factor is the relative humidity. So these gases, when your sensors are exposed to these gases, it's not just the gases in the atmosphere. There's also the issue of humidity. So we exposed our sensor to different percentages of relative humidity, from 10% up to 90%, and the response dropped. So the drop in this resistance is that now there's a competition on the surface of the material between the water molecules from the relative humidity and also your target gas and also the oxygen from the ambient. So we also had to compare the sensor performance of our material with some of the works that has been done on ethanol sensing from literature. And comparing the parameters that we obtained, we found that our sensor had actually good parameters. So it can actually be a potential to be applied for the detection of ethanol, but there's still some work to be done on it. So in summary, the nanofibers demonstrated great selectivity to ethanol, along with the sample having the highest amount of cerium, achieving a response greater than twofold than the pure lanthanum cobaltite at an operational temperature of 100 degrees Celsius, as well as a rapid response and recovery time of 17 and 32 seconds. And the sensor based on this cerium loaded lanthanum cobaltite nanofibers, particularly the one which is highly loaded, could be considered as a prospective energy efficient material to be utilized for low levels of ethanol molecules detections in applications such as food shelf life monitoring in the food industry. So when I say food shelf life monitoring in the food industry, is that ethanol can be used for shelf life monitoring of products such as mango, where you look at concentrations in the range of 10 to 200 ppm, and ours falls within that range. And so for the future work, we need to look at lower concentration of ethanol, which is going to be at concentrations lower than 1 ppm, because if you remember, we're starting at 2.5 ppm. And we also have to include ethylene, especially for selectivity, since in the food industry, especially for fruit and vegetables, ethylene is considered one of the gases that play a big role there. And then we need to do more stability tests over a longer period of time. So I'd like to acknowledge the Sensors for Food Safety Group, the Center for Nanostructures and Advanced Materials Characterization Facility, Council for Scientific and Industrial Research, the Department of Science and Innovation, and also the CSIR conference for giving me this opportunity. Thank you.
Thank you, Dr. Katekani. Very nice presentation, and you are very good teacher as well. I can see you very good teacher. So it's quite impressive as always.
Thank you so much for the wonderful presentation. I saw when you were doing the temperature studies, you started from 30 all the way up to above 100. So I'm thinking maybe in a winter season where you have temperatures that are below 30, what happens to the sensor now?
Okay, thank you for the question. So what happens is that operation temperature, it's actually operation temperature for the device. So it's sort of determination whether your sensor will need a battery or not, or the reactions can happen all by themselves. So there's the environmental temperature, which is your overall environment, and the device battery temperature. So that's what we're looking at. Yes, so but that's a good point. That's something that we should actually consider looking at. Thank you.
Any more question? Okay, there is one.
It's not a question, but it's a follow-up to what that gentleman has just said. So ideally, in handling fresh produce, we consider temperatures between 0 and 4 degrees. So I think apart from considering relative humidity on the efficacy of your sensors, look into the temperature ranges if they affect your detection. So maybe look at temperatures from 0 to 4 degrees, because if you look into fresh produce, most of it that is shipped is within that temperature. So I think that's one thing that you have to consider.
Yes, thank you very much for that comment. Thank you very much. We'll consider that.
Any more questions? No question. I'm very impressed, and we are very good and for future researchers that are upcoming. Very quality. They know what they are doing, and they're proud and confident to give presentation. It is very impressive. So let's thanks to all of our speakers, and thanks to all of you to come and support our speaker. So thanks and enjoy next session.